In the previous video, we discussed the expenditure minimization problem as an alternative model for the consumer's choices. And we showed how this model is closely related to the utility maximization problem. In particular, we discussed the graphical solution to the expenditure minimization problem, where the expenditure minimizing consumption bundle is just this tangent point along this desired indifference curve that is tangent to some straight expenditure curve, where the slope is just determined by the price ratio of P1 over P2, or the marginal rate of transformation, just like a budget constraint. In this video, we will solve an expenditure minimization problem with a Cobb-Douglas utility function as an example, using a full algebraic approach. By solving this problem from a slightly different perspective, the exercise will deepen our understanding of the intuition behind the model and the analysis. Now, just like before, we assume in this model that we have a consumer whose preferences can be represented by a Cobb-Douglas utility function. The prices for the two goods are P1 and P2, which the consumer cannot influence. And the consumer's choices in quantities must deliver a minimum utility level of U bar. The question is, how does the consumer choose these quantities in order to minimize the expenditure? Well, we have never encountered this problem before. But as we mentioned briefly in the previous video, this is just another constraint optimization problem with a single constraint. The difference is that now we're trying to minimize the expenditure as objective as opposed to maximizing the utility. Now let's try to write down our problem in the form of an optimization program. Just like before, we need to write down our objective and our constraint. The objective here is just the total amount of expenditure we'll incur on these two goods of Q1 and Q2. And we're trying to minimize it by choosing this pair of quantities Q1 and Q2. The constraint in this case is that the utility delivered by these two quantities combined must reach this desired level of U bar, which is now an exogenous variable. In particular, as we have argued in the previous video, in order to save expenditure, the consumers won't choose a bundle that offers any extra utility above U bar at the optimum. Therefore, the constraint can be treated as an equality. And now we have an optimization problem with a single equality constraint. And we can just use a Lagrangian to solve it. Well, when we spent a lot of time explaining the Lagrangian approach in earlier videos, I promised that it will be used repeatedly in this course. And you bet I'll deliver on that. All right, let's get started. First, let's write down the Lagrangian based on the optimization program. The Lagrangian here is again just the objective function plus lambda times a cleared out version of the constraint. Here I subtracted the utility level from Q1 and Q2 from this fixed level of U bar. You can do it the other way around. It doesn't change the end result at all, although the algebra will have slightly different signs along the way in the first order conditions. And now with the Lagrangian in place, we're going to take derivatives with respect to the two control variables Q1 and Q2 and lambda, and that will give us three derivatives. By setting these three derivatives to 0, we found three first order conditions. The first two first order conditions are essentially the price of the goods minus lambda times the marginal utility of that good. And they have to be 0. While the third first order condition is just the recovered utility constraint. We'll try to use these three conditions to solve for the unknowns of Q1 and Q2 as our optimal consumption bundle that minimizes expenditure. To do that, we're going to use the same trick as before, where we try to combine the first two first order conditions into one equation. We will move the negative term to the other side of the equality, and we'll end up with these two expressions. And then we're going to divide the left-hand side by the left-hand side and the right-hand side by the right-hand side. And surprise, surprise, we get the tangent condition again. With its marginal rate of substitution, the slope of the indifference curve is equal to marginal rate of transformation, the slope of the expenditure curves. As we have done in the utility maximization problem, now we can rewrite Q2 in terms of Q1 in order to substitute into the constraint or the third condition. Of course, you can do it the other way around to write Q1 as an expression of Q2, but that wouldn't really matter for the end result. All right, so here we're going to rewrite Q2 as an expression of Q1 and exogenous variables. And by the way, this is exactly the same expression that we have gotten for the Cobb-Douglas utility function in the utility maximization problem. All right, now we're going to substitute 4 into 3 and then solve for Q1. All right, let's look at the substitution. In equation 3, we have u bar minus q1 to the power of alpha times q2 to the power of 1 minus alpha is equal to 0. And now can plug in the expression of q2 into equation 3 here. And that will give us u bar is minus q1 to the power of alpha times 1 minus alpha over alpha times p1 over p2 times q1 raised to the power of 1 minus alpha. Once plugged in, we can treat this entire term in front of q1 within the parentheses as a big package, and then just distribute the power of 1 minus alpha to the package and then to q1 separately. So what it looked like is the following. This equation is equivalent to u bar minus q1 alpha, and then the power distributed to this package and to q1 separately. And now you can see that we're able to combine the q1 term here and the q1 term here. In particular, you realize that we can rewrite q1 to the power of 1 minus alpha as q1 to the power of 1 times q1 to the power of minus alpha. And then, because this term has q1 to the power of alpha, and now we have a q1 to the power of minus alpha, they will just cancel out. And now what we have suddenly becomes linear equation of q, because we have u bar minus this package 1 minus alpha of alpha times p1 over p2 to the power of 1 minus alpha times q1 is equal to 0. And to solve for this, we can just move u bar to the other side of the equation, multiply both sides by minus 1, and that gives us this expression on the right-hand side on the slide. And then what we can do to solve for q1 is just to multiply the reciprocal of this entire package on both sides of the equation. And the reciprocal would just be the same package, but raised to the power of alpha minus 1. And so the result of the solution is just q1 star is equal to this package raised to the power of minus 1 times this, which is alpha minus 1 times u bar. And there we have it. This is the expenditure minimizing quantity for good 1. Now, having solved for q1 star, we can plug it into either equation 4 or equation 3 here to solve for q2. And here, I chose to plug it into equation 4 here. Well, in equation 4, we already have q2 is equal to this package times q1. And once we substitute in q1 star into this position, what we have is that package times this package again raised to the power of alpha minus 1 times u bar. And then again, you can see this term with the parentheses and the power as the package raised to the power of alpha times the package raised to the power of minus 1. And of course, the minus 1 part will just cancel out with the package in the front with the power of 1. So the result is just a package raised to the power of alpha times u bar. And there we have it. This is the solution for good 2. And it is our q2 star here. Summing up for now, we found the expenditure minimizing choices for a Cobb-Douglas utility function with a preference parameter of alpha is Q1 star is equal to this expression and Q2 star is equal to this expression. These quantities are functions of the exogenous variables. The prices P1, P2, the desired utility level we have to hit, which is U bar, and the preference parameter of alpha. In other words, once you tell me what are the prices P1, P2, what is the target utility level I have to reach, and what is the preference parameter alpha, these functions immediately tell you what are the optimal choices in quantities that will minimize the expenditure for this particular consumer. Does that sound familiar? Well, yes, these are also derived demand functions, but they're derived from the expenditure minimizing problem. So unlike the derived demand from the utility maximization problem, they don't map from prices and the budget to quantities, but they map from the prices and the target utility level in order to minimize the expenditure. I'll come back to this note later. Now, just like we can plug the derived demand that maximizes utility level back into the utility function to find the resulting level of utility and derive the indirect utility function, we can do the similar thing here. What we can do is we can plug in these optimal cost minimizing quantities into the expenditure expression to find if we have to reach this utility level of U bar and we have to pay these prices of P1 and P2, what is the minimum amount of expenditure that we have to spend in order to make that happen? Because we have already found the consumption bundle that minimizes expenditure. So just calculating the cost on this consumption bundle is exactly that expense. So here, what we're doing is plugging in the expressions of Q1 star and Q2 star that we have just found on the previous slide back into the expenditure expression. So we're just multiplying the quantities by their respective prices. And the resulting expression should tell us what is the minimum level of expenditure we need to spend in order to get to this utility level of U bar. We can do some algebra to combine these two expressions together and make it cleaner. But all these steps are just algebra. And I'll come back to this in a second. But now let's focus on the result of this calculation here. Notice that it is a function of exogenous variables describing the decision environment, which are just the prices, the preference parameter of alpha, and the target utility level of U bar we have to hit. Just like the indirect utility function, this function embeds all the optimal consumption choices, and it maps these parameters directly into the minimum level of expenditure needed to achieve that particular utility level, given these prices of P1 and P2. So we will call this function the expenditure function. As of the algebra going to the simplification from the second line towards the end, what I did here in the second line to the third line is that I distributed the powers of alpha minus 1 and the power of alpha into these expressions because I want to combine P1 here with P1 here and combine P2 here with P2 here. And in particular, I'm treating this ratio of 1 minus alpha over alpha as a combined term. So the result is that I have 1 minus alpha over alpha raised to the power of alpha minus 1 times P1 to the power of alpha minus 1 times P1. So the minus 1 power and the power of 1 cancel out, and we're just ended up with P1 to the power of alpha. On the denominator, it is just P2 to the power of alpha minus 1 that we have here. And the same calculation holds for the second term, where the power alpha goes to this term, this ratio of 1 minus alpha over alpha, And then P1 receives the power of alpha, P2 receives the power of alpha, but then it is multiplied by a power of 1. So effectively, we have P2 to the power of 1 times P2 to the power of minus alpha, because P2 here is on the bottom. So combining them, you have P2 to the power of 1 minus alpha, or flip it to the bottom, you have P2 to the power of alpha minus 1. So now, what I noticed is that this expression here on the left is exactly the same expression as this one on the right-hand side. So what I did is that I tried to factor them out. Now, once I factor out this expression here, the inside becomes 1 minus alpha over alpha to the power of alpha minus 1 plus 1 minus alpha over alpha to the power of alpha. The entire thing is multiplied by this common factor of P1 to the power of alpha over P2 to the power of alpha minus 1 times U bar. Now, once I have this expression, I realized that I can also rewrite this expression slightly, and hoping that will look very much similar to the second term. And to do that, I can open up the powers in the first term, and it will look like 1 minus alpha over alpha to the power of alpha times 1 minus alpha over alpha to the power of minus 1. And then it's added to this same ratio of 1 minus alpha over alpha to the power of alpha. And then times our term on the outside, which is P1 to the power of alpha over P2 to the power of alpha minus 1 times U bar. And now I have another term I can pull out, which is the ratio of 1 minus alpha over alpha to the power of alpha. Once that's pulled out, on the inside, I have the expression of 1 minus alpha over alpha to the power of minus 1 plus 1 times 1 minus alpha over alpha to the power of alpha. And then, of course, multiply by P1 to the power of alpha over P to the power of alpha minus 1 times U bar. And then on the inside of the square brackets, this ratio to the power of minus 1 is just flipping it upside down. So then I'm going to have alpha over 1 minus alpha plus 1 times 1 minus alpha over alpha to the power of alpha times P1 to the alpha, P2 to the alpha minus 1 times U bar. And now inside, we can simplify and try to combine this ratio with 1. And that will give us 1 minus alpha on the bottom. On the top, it will be alpha plus 1 minus alpha. And that will be the case where alpha and minus alpha cancel out. So on the inside of this bracket, we'll just have 1 over 1 minus alpha. On the outside, we also have 1 minus alpha. So I will try to combine these 1 minus alphas. To do that, I need to distribute the power on this ratio now to their separate parts of 1 minus alpha and alpha. And what I'm going to do is on the top, I'm going to have 1 minus alpha to the power of alpha. On the bottom, I have alpha to the power of alpha, and then times exactly the same thing, P1 to the alpha, P2 to the power of alpha minus 1 times U bar. Now, what I have is just 1 over 1 minus alpha, or 1 minus alpha to the power of minus 1 times 1 minus alpha to the power of alpha. And that is 1 minus alpha to the power of alpha minus 1. The power minus 1 is coming from the bottom term here. The power of alpha is coming from the term up there, all right? And then I have this term divided by alpha to the power of alpha times P1 to alpha, P2 to the power of alpha minus 1 times U bar. And that is our line here. And the last step is just to notice that I have alpha here and P1 here that shares the same power of alpha. and 1 minus alpha here, and P2 here shares the same power of alpha minus 1. So I just try to group them up and pull out those powers, and that looks slightly nicer. And that's this expression here at the end. There is really no economics intuition involved in these simplifications, but it does help me get more familiar with manipulating these expressions and improves my familiarity with these objects. One very important message we highlighted when we discussed the graphical solution of the problem and its dual relationship with the utility maximization problem is that they lead to the same optimal choices. And the resulting expenditure will turn out to be the budget Y that we started with in the utility maximization problem. However, the key to all of the duality results is that, as we have emphasized repeatedly, that we cannot just set any arbitrary utility level to reach and then hoping to get exactly the same budget as the expenditure. Graphically, we really have to start at this particular utility level that we need to reach, which is the ending result of utility maximization problem. And we have to grab this indifference curve and drop it into exactly the same spot on the right-hand side graph, now as our new target, and then try to minimize expenditure from there. And then we will be able to land at the same consumption bundle as before, and then land at the same expenditure level as the budget that we had before in the utility problem. Only then the duality properties will appear. In fact, this is why the demand functions we found as the solutions to the expenditure minimization problems look very different from those we derived from the utility maximization problem with a Cobb-Douglas utility function. If you remember, for the Cobb-Douglas utility function, the demand we derived back then is that Q1 is going to be alpha share of the budget Y divided by the price of P1. And similarly for Q2. These expressions look nothing like that. So how do you reconcile the differences in these expressions with all these intuitions that are saying they should be at the same value if we set particular things in particular levels? Well, we're going to wrap up this expenditure minimization problem by verifying that algebraically, indeed, these quantities are identical. But the essential piece is that we have to start from the optimal utility level that is a result from the utility maximization problem when we started with a budget level of Y. If we pick this particular utility level of U bar to minimize expenditures, then we will see the duality properties. And the quantities will land back to exactly these Q1 star and Q2 star that we had before. And hopefully we can see that algebraically as well. To do this, we need to make use of an object that we derived previously, which is the indirect utility function. We know from our previous work that when we choose optimal consumption bundle that maximizes utility, the resulting utility level is given by the indirect utility function. In fact, we derive this function by plugging in those optimal demand functions into the utility function to find this expression. If this doesn't ring a bell, you can review the indirect utility function by watching the previous video on the reflection of the Lagrangian approach. Now let's try to verify that expenditure minimizing quantity for good 1 that we have derived, which looks like this, is in fact identical to the utility maximizing quantity we found before from the utility maximization problem that looks like this. But remember, we will need to look at the expenditure minimizing quantity when the target utility level is a very special level. The level that we obtained when we had a budget of Y. But what's that utility? Well, that's exactly given by our indirect utility function of V. It tells us the highest level of utility we're able to reach, given prices P1 and P2, and we started with the budget level of y, is u bar. Graphically, the v function tells us that given this budget level of y and the prices P1, P2, the level of utility we're able to reach and the best possible scenario is going to be measured by u bar, which is exactly the value given by this v function here. Now, what we're doing on the right-hand side algebraically is literally grab this level of utility and drop it in as our premise to minimize expenditure. And that's what we're doing. We're taking a value of utility expressed by a very specific indirect utility function and drop it into this utility target. And then Q1 star here that we already solved for will tell us what is the optimal level of good 1 that will allow us to reach this indifference curve that has a utility level of u bar, given these prices of P1 and P2. So this is why we're moving from step 1 to step 2 here by plugging in this indirect utility function of v into the spot of u bar. And from our previous work, we already found that the indirect utility function in this case is taking this particular expression, and this is why we're plugging in this particular expression into the spot of u bar, and that is this part here. All the economics are in this step, where it is the definition and interpretation of these objects that dictates the way we use the math. The next two steps are just algebra. From line 2 to line 3, I just noticed that the first term in parentheses contain the same ratios essentially as the second and the third terms. We have 1 minus alpha over P2 already, and we will have alpha over P1 as soon as we add a negative sign to its power. So what I have in mind is I would like to split up the first term into 2 terms and then combine them with the second and third term. And that's what I'm doing from line 2 to line 3. From line 2 to line 3, you will realize this part is exactly the same as this part, because that's just the part that to be combined with the first parentheses. And what I'm doing is really just breaking up the first parentheses into 2 terms and also make them look like third and the fourth term. Okay, so once you split up the first term into these 2 separate terms, we're able to just combine them by their power. Again, the power of minus alpha and the power of alpha cancel out between the first and the third term. So we're just left with alpha over P1 to the power of 1. And the second term and the fourth term are exactly reciprocals to each other. So they will just cancel out with each other. At the end, we're just left with alpha over P1 times y. And that's our solution. And that's exactly the demand function we found when we solved the utility maximization problem. A very similar calculation will verify the same case holds true for Q2 star, and I'll leave that to exercise. In addition to verifying the quantities, we can also verify that if the highest level of utility we can obtain, given the level of budget, y is this level of u bar, then the minimum level of expenditure we have to spend in order to reach u bar is also y. To verify this, we need to make use of the expenditure function that we just derived. Remember that the expenditure function directly tells us that the minimum amount of expenditure we need in order to reach this level of utility of u bar when the prices are P1 and P2. In this case, we want to check what is the expenditure needed to reach the maximum level of utility we could get when we had a budget level of y and facing prices in P1 and P2, which is given by the indirect utility function. So just like the last slide, we will plug in this expression into the spot of u bar, and that gives us this expression here on the third line. The algebra here is very straightforward. We realize immediately that the first term is the reciprocal of the third term and the second term to the fourth term. So they cancel out with each other perfectly, and we're just left over with the expression of y at the end. So we have verified the intuition that the minimum level of expenditure to reach this optimal level of utility of u bar when we had a budget of y is indeed a level of expenditure at y. Now we have worked closely with the utility maximization problem and the expenditure minimization problem, and we explored their connections with each other. It is useful to compare and contrast their derived demand functions very closely as well. We have essentially derived two different kinds of demand functions. From the utility maximization problem, where the budget y is limited, we derived demand functions that are chosen to maximize the utility. These demands are conditioning on the prices and the limited budget level. Therefore, the functions of prices and the budget level. We call this function the Marshallian demand function, or uncompensated demand function, where the budget or income is held constant. On the other hand, from the expenditure minimization problem, where we have to reach a fixed level of utility, the derived demand functions are chosen to minimize the expenditure level given the prices and this target utility level. Therefore, they're functions of prices and this target utility level of u bar. We call this type of demand functions the Hickson demand or compensated demand, where we guarantee a level of utility, but the expenditure is somewhat flexible. These demands coincide with each other when we set one problem's outcome as the constraint of the other. In our previous exercise, we verified with a special case of Cobb-Douglas utility function that when we set the target utility level of u bar to the outcome of the utility maximization problem, the Hickson demand becomes exactly the same as the Marshallian demand. And a similar exercise works the other way around as well. If you set the budget level y in the utility maximization problem to be the resulting expenditure level in an expenditure minimizing problem E here, then the Marshallian demand will also turn out to be the same as a Hickson demand. So far, what we've done is essentially a pair of parallel derivations. We started from one of the dual problems and derived their respective demand functions. The utility maximization problem derives Marshallian demands, which are functions of prices and y. The expenditure minimization problem derives the Hickson demands, which are functions of prices and u bar. We then plug these demands back into the objective functions to find the resulting levels of maximized utility described by the indirect utility function v, or the level of minimum expenditure needed, which is described by the expenditure function e. One question is that we derived v and e from the demand function, but can we go backwards? In other words, if we have v or e, can we derive the demand functions from them? Well, the answer is yes. And these results are actually very useful. So useful that they have their own names. The result that allows us to recover the Hickson demand from the expenditure function is called the Shepard's lemma, and the result that recovers the Marshallian demand from the indirect utility function is called Roy's identity. Now let's look at these two results. We will present these results as theorems. Let me first describe Shepard's lemma on the notepad, and then I'll explain the formal statements in the slides. An expenditure function E is a function of the prices, P1, P2, and the target utility level of U bar. Shepard's lemma simply says that if we take a partial derivative of the expenditure function with respect to P1, we'll get the Hickson demand for good 1. So what happens is, according to Shepard's lemma, if we take a partial derivative of the expenditure function with respect to P1, we will recover the Hickson demand for good 1, which is again a function of P1, P2, and the target utility level of u bar. And similarly, this works for good 2 as well. If we take a partial derivative again of the expenditure function, which is function of P1, P2, and u bar with respect to the price of good 2, which is P2, then we're going to end up with the Hicksian demand for good 2, demand that minimizes the expenditure level. And it is, again, just a function of the prices, P1, P2, and u bar. And that's it. In other words, if we have a good in mind, good 1 or good 2, then just take a partial derivative of the expenditure function with respect to the price of that good you have in mind, you can get the Hicksian demand back. The striking part is really how a simple derivative recovers the demand from the expenditure function. Now let's turn to the formal statement on the slide. This expression here looks really scary, but it is really just a lazy way to write these two expressions on the left-hand side in one go to save space. We have an expenditure function here on the top, which is a function of prices of two different goods, one labeled I and the other one labeled minus I. Minus is not really minus, just means not. So if I is good 1, then minus I is good 2. If I is good 2, then minus I is good 1. Okay? And what we're saying is simply that take derivative of the expenditure function with respect to the price that you have in mind, then you're going to get the Hicksian demand for the good you have in mind back. That's it. This good can be 1 or can be 2. And when you do it for one good, the price of the other good is also going to play a part in here, and it's going to play the part through this other price of P of minus I. At this point, we won't provide proofs for Shepard's lemma, but we will illustrate how it works. For instance, we have already derived the expenditure function for the Cobb-Douglas utility function in our previous exercise, and we have also derived the Hicksian demand functions. So now let's try to use this equation in Shepard's lemma to verify that indeed, if we take a partial derivative of the expenditure function with respect to the price of good 1, then we can get this Hicksian demand back. Can you pause the video here and take a few minutes to give it a try? Please do that. Now, if we take a partial derivative of the expenditure function with respect to P1, the only term that is affected by P1 is just the first term. So the second term and u bar will just remain there as a constant multiplier. And to deal with the derivative, we'll just use the chain rule to find the derivative with respect to P1. Treating the inside ratio as a whole package, the derivative of the package raised to the power of alpha with respect to that package is just alpha times this ratio, this package, raised to the power of alpha minus 1. And then the second part of the chain rule is just the derivative of this inside package with respect to P1, which is just 1 over alpha. And the remaining part is just this expression taken as it is and put here as a multiplier. And there we go. Now we can notice that the alpha here on the denominator cancels out with alpha here. And we also notice that if we flip the P2 over 1 minus alpha upside down and slap on a negative sign on the power, we can combine these two terms into one. And that's precisely the Hicksian demand expression we derived from the previous example. You can also give it a try for good 2, and you should be able to verify that Shepard's lemma also works there. Now let's turn to Roy's identity. The statement of Roy's identity is slightly more complicated, but basically in the same spirit. Let's look at it here. Essentially, what we have is an indirect utility function that tells us what is the highest level of utility we can reach when we have prices of P1 and P2, or Pi and P minus I here, and a fixed budget level of Y. So the Roy's identity says, if we take a partial derivative of the indirect utility function with respect to the price of a particular good you have in mind, 1 or 2, and then divide that derivative by the derivative of the indirect utility function with respect to the budget level Y, Then you add a negative sign in front, and we are going to recover the Marshallian demand function. Let's verify that Roy's identity works. So here, I copy-pasted our previous results of the indirect utility function from the Cobb-Douglas utility function, as well as the Marshallian demand function here. So we can verify, hopefully, that by taking derivative of the v function with respect to p1, and then divided by the derivative of v with respect to y, and then multiplied by -1, we're able to get this expression back. The algebra for the derivative of v with respect to p1 is very similar to the last slide, and chain rule will give us the result on the numerator. The derivative of v with respect to y is just the first two terms in the parentheses, so we have the denominator. Multiplied by the negative sign in front, we see that the negative signs will cancel out, and this ratio of 1 over alpha over p2 to the power of 1 minus alpha will cancel out exactly with this term on the bottom. And we can also see that we have alpha to the power of alpha on the bottom, which will cancel out with this expression on the top. And we'll also have a p1 to the power of minus alpha. They'll cancel out with p1 to the power of minus alpha here on the numerator. So we're just left with alpha times p1 to the power of -1 times y, which is just alpha times y over p1. Exactly the Marshallian demand functions we're familiar with. Now, with the Roy's identity and the Shepard's lemma, we can augment the relationship among these objects slightly. We notice that the Marshallian demand functions can derive the indirect utility functions, but also we can derive it backwards from the indirect utility function through Roy's identity. And similarly, Hickson demand functions can derive expenditure functions, but also it goes backwards through the Shepard's lemma. To put differently, in this very long section of the course, we started with three basic axioms of consumer choices: completeness, transitivity, and non-satiation. These three conditions pin down the properties of the indifference curves. We then use some utility functions to represent these indifference curves, which provides the tools necessary for us to model the consumer's choice problem. We explored two alternative models. One maximizes utility subject to a budget constraint. The other one minimizes expenditure subject to a utility target. Each model derives its own associated demand functions. And these demand functions derive indirect utility functions and expenditure functions that tell us the ending result of these optimal choice problems, given their decision environment described by prices and budget, or prices and the target utility level. And from there, with the help of Roy's identity and Shepard's lemma, we can also derive the demand functions again from the results. These objects are very closely related to each other, and the demands on each side coincide with each other in very special conditions, as we have verified. In the next section, we'll build on these elements as a foundation to develop more economic intuitions about the consumer's choices.